singularity analysis.
Thank you, Mr. Sherman, for the presentation. This is the table of contents. It will be short, just an introduction, then the code itself, the semi-analytical code, some feature of this code and the numerical result, and to end with the conclusion. As it is well known, when several materials with different material conditions meet, there are the stress field can have a singularity. This singularity depends not only in the material characteristic but also on the boundary condition and on the geometry of the structure. This can be a real problem because you can find this kind of singularity in the, for example, in the aeronautical industry. This is because each time the composite material and the bonded interface are more uses in this industry. And just here, that is two composite material bonded to a metal, there are several corners like this, where you can find different structure with singularities. Also in the microelectronic, where the union of different materials can bring to a singularity also for the stress field due to the change of temperature. We can see that just in this short, in this small piece, there are all these kinds of possible singular points. In the manufacturing of pieces, when you put out material, due to the friction of the tool with the material itself, you can also find different singularity. All these effects change the singularity itself and must be calculated. Some authors, as Sinclair, have particular singularity for each case. Solution for unimaterial and multimaterial isotropic corner for different boundary conditions. Shen, Gonzalez, and they claim they have particular solution for geometries, for some geometry, for an isotropic material corner. But other authors have put all their effort in develop a code that are more generic. For example, Papadakis, Yoshivas, and Kostabel develop different codes that are able to solve at the same time when you choose the parameters. Single and multi-material corner for isotropic or anisotropic material in 2D or 3D, depend, but only for newer or English-led conditions and for perfectly bounded interface. On the other hand, Lee and Barber were able to develop a code that could solve more type of boundary condition. For example, frictionless contact or frictional contact, both in the interface and in the boundary, but only for isotropic material. This made this lack of a general code that is able to solve every kind of material, of linear elastic material, for single or multi-material corner, for general boundary condition, including symmetry, anti-symmetry, frictional contact. This was us to develop a code able to solve all this kind of problem. This code has been already verified with the comparison of the result with many other authors or analytical solutions that I say before for the particular cases. It has been verified successfully. The objective of this work is just to show all the features that this code has and if the code itself. First, we start with a little bit of the nomenclature that I will use. This is a multi-material corner for us. When you have only one material, we not bonded to another one, just with an interface that can be frictional or frictionless. We call it wedge or single wedge. When there are several materials bonded, perfectly bonded, they said, we call it multimaterial corner, multimaterial wedge. The code is able to solve single material and multimaterial corner for open corner and closed corner. An open corner is when it has a boundary condition, not only the interface condition. A closed corner is when it only has interface condition. The main objective of the code is to solve the displacement field and the stress field in the multimaterial corner or the single material corner. Here, the singular exponent is called lambda and is one of the parameters that we have to search first. When there is a frictional contact, for example in this corner, and you can see that there is contact between the both material but they can move, we define also another parameter that is omega. Omega is the sliding direction or the shared direction, that one opposed to the other one. Now the code structure and theoretical background. The theoretical background of this code is it is based on the stroke formalins, the transfer matrix of T, and the matrix formalin of Mantič. All this is well explained in these two papers that are already published. The first one, the second is under review, because it's impossible to say all in here. The code is divided in 6 modules. The first one is the data input, where the user will introduce all the material properties, the type of corner, and the boundary and interface condition in the corner. It can be introduced through a pre-write file or in an interactive way. The code will be asking for the properties of the corner. When the code knows all the properties, it will calculate the stroke matrices A and B for every material, and with them the transfer matrix E. With the boundary and interface condition and the number of material and the angles of the materials, it will calculate the reference frames for each material and for each wedge, and the boundary condition matrices and interface condition matrices. Once that the code has all of them, it can start calculating the characteristic system of the corner. First, with all the transfer matrix, it will calculate the transfer corner matrix, that is the K, and with the boundary condition and the interface condition, it will calculate the main matrix of boundary and interface. By multiplicating them, it gets the K corner, that we call K corner, that is the main matrix of the corner. By solving it, in case that there is no friction, we get directly lambda, and when there is friction imposed in some of the interface or boundary, we have to calculate also omega directly from here. By substituting them in the matrix, in the main matrix, we go into the post-processing and we get directly the displacement and the stress in all the angles that we want. Now we will spawn the code feature and some result. The first feature is that the code is able to calculate the number of singularity in a range of lambda value. We always more or less always calculate it from 0 to 1 because it's the normal values for lambda, but it is possible to calculate all the range. To calculate it, we solve, this is the cut corner, the main corner that I said before. And just by calculating the determinant, we can see here the real part of the determinant. When it has a 0 value, there are the solution. In this case, there are these two solutions. But what happened with this point? This point can be also a solution because lambda can be a complex value. And in this case, by by calculating also the argument principle, it will say that here there is also a solution. So in this case, we have two solutions plus a pair of complex values of lambda. When there is friction in some of the interface of boundary, it is not possible to calculate directly by the determinant. So we have to calculate a single value decomposition of this main matrix. As it depends on lambda and omega, the slide item that I said before, that it depends also on it when there is friction, we have to draw a map with the values of the sigma of the singular value decomposition versus the lambda and omega, and we will find in the darker value where the value of the sigma is lower the possible solution. In this case, that is a 300-degree corner with a frictional boundary in θ0 and clamped in θ1. We have 11 possible solutions. This solution, some of them will be physically possible, or some of them not, because the shell stress must oppose the sliding direction, and this we will calculate in the last module of the code. But first, we have to calculate the real singular solution here. Here we have 4 cases. This is a bimaterial corner with, in this result are in the case that this interface here is bonded, and this case, this result are when this interface is underbonded. This change can be made only by changing one parameter of the program. You don't need to have different equations, it's just directly. And you can see the difference in the time, the computing time. Also, the difference between this and this case is the position of the fiber, because when you have an orthotropic material, you can move the fiber of the material to have a monoclinic material or an isotropic material. And the result check, the time consumed by the computer change, because the transfer matrix is heavier than for an orthotropic material or isotropic material. This is the same, but with 3 materials. It is easier to go adding more and more material, and the software will have no problem. It will just consume a little bit more time, but it is not a big problem for the code. The last this is all the possible cases that can be solved and that have been solved. It could be more, because we can add all the material that we want. As we said at the beginning, the goal of this code is to be more general than all the other that were already done. So we can solve singular multimaterial and linear elastic behavior for boundary condition free, Klepper, friction, symmetry, antisymmetry, only one displacement direction, or only forbidden one of the direction of the slider with the interface condition, perpendicular, frictionless, or frictional. All the results that we have got have been compared with analytical expression found in the literature, and we had at least 10 digits of coincidence with them. So this assures us that the code is very flexible and you can trust on the result. The last module now is the code shows the stress and displacement field. This is an example of all that we can solve. Here we have a bimaterial corner with the stress free in the boundary condition and with a friction interface here. In this case, the frictional coefficient was 1. The solution for this problem is this singular exponent and this sliding pendulum. And we can see here in the displacement field, for example, that it matched with the boundary condition that we have imposed, because you have a displacement in the minus 180 degrees and in the 90 degrees, and you have here in the θ0 a contact because the u theta, the normal displacement, is constant from in the jump from one material to the other, that is zero. But the tangential displacement that are u r, the blue one, and u3, the yellow one, has a jump. This also can be seen in the stresses. This is the last. The conclusion now. So just to say that the developed code for singular analysis of an isotropic and multimaterial corner it has demonstrated to be efficient and accurate. It's useful to improve pen solution and has a huge variety of functions. The tool is up for future. The tool will be available in the website. And that is all. Thank you for your attention. Do you have any question or anything?
Must be really
Yes,
fast.
yes.
I have a question.
Yes.
What programming tool do you use to develop
The
your
code is in MATLAB.
Sorry?
The tool is programmed in MATLAB. It's a code in MATLAB. Yeah. We were thinking of doing it in Python to put it in the website in a faster way. Yeah.
Okay, thank you very much.
Sorry.